Hello and welcome to Deep Learning with Pytorch Lesson 12. We're going to finish up Chapter 7, which the chapter itself is quite simple. I think we got about halfway through it in the last video, but the code is a little bit complex, the code associated with the chapter. So we're going to go through it real quick. It shouldn't take too long. Some of the code I couldn't get it to work, but the main ideas of it are pretty simple. So I'll go through the chapter a little bit right now, and basically, yeah, we're creating a neural network to decipher between airplanes and birds through the images. This is where the code where we are taking the Cfar10 data set and switching it to a Cfar2. Here's the fully connected model. What it's showing here is that however many nodes we have, each pixel within the image has to go to each node, and the output would be a probability. Here's their first neural network. So in out is 2. You got 3,000 layers. So you got to imagine why the training takes so long for this network is because there are 3,000 nodes in there and 512 in the second layer. So that's quite a bit. Every pixel goes to every one of those nodes. So it exponentially, or well, I guess exponentially might not be the right word, but it increases substantially. Like you have to multiply them. And we'll see an example of that in this code as well. Here's the softmax. We talked about that to get the probability of each layer. This is the formula for calculating the softmax. Let's keep going here. We're going to talk about batch sizes and how a neural network goes through it. And here's the NLL negative log likelihood function. And that's the best loss function for classification. So now we can modify our model to use NN log softmax and then initiate the NLL loss. So at the end we do a log softmax and then we do the NLL loss. But there's another way to do it too. I think it'll show us that in a minute, which will you can, instead of doing this and this, you could do it in one step. Here's just showing two loss functions. This is the cross entropy. We've already used that once. And here is on the right is the mean squared error. So actually, I don't think we've used this before. We were using the mean squared error. And this gives a little bit less steep of a gradient, so it's better for classification. And here's the example. Do they use? They're still using a loss function. So here, still linear layer, 3,000 to 512. Second layer has 512 to 2. 2 being the classification that we run through. Here's the learning rate. Here's the loss function is NLL loss. Number of epochs, they could print that. So I'm pretty sure everything's just getting fed into here. And now they're going to talk about this. This is an important figure here. Because A, for n epochs, every sample of the data set, this is how it goes through it. It goes evaluate the model, compute the loss, accumulate the gradient of the loss. So you go through and accumulate the gradient of the loss here for every sample in the data set. And update the model with the accumulated gradient. So C is where we split it into mini batches. So for every mini batch, not for every sample, for every mini batch. So a mini batch could be 4, 5, maybe 6, and even more than that, images all being fed through at the same time. So if you increase your batch size, it will train faster. But if your batch size gets too large, it will eventually may possibly lose some accuracy because you're training it on multiple images at one time. So with every sample in the mini batch, it will evaluate the model, compute the loss, and accumulate the gradient of the loss, and then update the model based on that. So for every sample in the mini batch, so it'll only do this after the mini batch is done. So, I mean, technically, you could picture it, feeding in an image, then the next image, then the next image, then say it's a mini batch of 4, it'll feed in all 4 of those images, and then it will update the model with the accumulated gradient. If you just do it for every sample, so what you could consider every sample to be is a mini batch size of 1. So your computation speed will increase, right? Because after each image that goes in it, it will start the iteration over. Whereas with this one, 4 images go through it, and then it updates all the numbers inside of the neural network. And I don't know what B is supposed to be. For n epochs, I mean, it looks like B is compute loss of gradient. So A is averaging updates over the whole data set. B is updating the model at each sample. Oh, so it doesn't clear the gradient. So A is an example of it not clearing the gradient. It's just taking the average of the gradient as each sample goes through it, and then after that full epoch, it will clear the gradient. For this one, it's clearing the gradient at each sample, and then C is clearing the gradient after each mini batch. So that's important to understand these 3 architectures. And I think for the most part, you're going to be looking at the architecture style 3. You're almost always going to be using mini batches. It's just a much more efficient way to do it. Here's an example of how the gradient works there. So this is showing your update of the gradient over each mini batch. So it may go back and forth, possibly not in the most optimized way. And then this is gradient over all of the data. And here we have the gradient over the mini batch. So the mini batch is kind of a step function where the gradient over all the data is a smoother function there. Here's just an example of what the data loader does. Here's the batch size of 4. Shuffle equals true. So shuffle means that it's randomly grabbing 4. It's not just going, all right, take images 1 through 4. Take images 4 through 8. Take images 8 through 12. And so on. It's actually randomly grabbing 4 each time. Here's some more code here. And unfortunately, with these, I might try and run one and just decrease these numbers here because I don't know. I mean, I guess you do need it, but to get some good accuracy, but it won't train as fast. So if you're running this code and you want it to run a little bit faster, you could just decrease these numbers. And the only stipulation with creating your own neural network here is that you have to basically make sure this 512 equals this 512 or whatever number is here, because this is your output from layer 1. It needs to be the equivalent of the input of layer 2. And here they're seeing their loss function here. Batch size, blah, blah, blah. And at some point, here's the log softmax. Here is an important sentence here. The combination of in log softmax and in LL loss is equivalent to just using the cross entropy loss function. So what we have here is equivalent to what we have here. And what's the differences? Let's slow that down so everyone can see it. We're going linear. This is your nonlinear activation function, another linear layer, blah, blah, blah. And at the end, we perform a log softmax. So this is the output of the 2 probabilities. We put that in the form of a log softmax. And actually, there's no loss written here, but let's say there was a loss equals in dot in LLL loss, or in LL loss. This combined with this loss function is the equivalent of this code here. So there is no log softmax here. So it's kind of like, it's fine however you want to type it in, but in this way you only need this line. For this one you would need this line and then another line detailing the loss function that is going to be used. And these are the parameters. So this is showing how many parameters are within the code, and there's quite a bit. So it's showing each parameter at each layer here, how many calculations it has to do. I think you could word it that way. It says 3.7 million parameters. But that's not 3.7 million. That's oh yeah, it is. That's 3.7 million parameters. Not a small network for such a small input image, is it? And even the first network was quite large. And this was the one that was just 2 layers. And it was 1.5. So that's because each pixel has to go to each one of these. This 3,000 layer, 3,000 noded layer. It's an input of 3,072 and an output of 1,024. Each pixel is connected to each layer. So, I don't know, 32 by 32. I think we could do the math on this. Let's try it. 32 by 32 equals, and then we're going to multiply that. That's where we're getting the 1,024 by 3,072. 3.1 million. Okay, 3.1 million. That's where that number's coming from, 3.1 million. So that's what I mean about each node being connected to each pixel. So that's how many calculations it has to do per image. So that's a substantial amount of, arithmetic calculations or linear algebraic calculations. So that's why it takes such a long time to train. I think this is where it's showing it. The limits of going fully connected. There's one vector of weights per output pixel. All input pixels contribute to every output pixel. So it's quite substantial. And that's about it. So we can look at this code. Like I said, some of it didn't go through as well as I wished it would have, but we can even try and do some new things here. So we went through this code in the last video. Got all the way through to here, and then we stopped. So now we're defining our model here, our log softmax and our NLL loss. So remember, one thing we could have done is just delete this and have the cross entropy in cross entropy loss function there. And that's how that's written. But we're doing it this way, so that's fine. Image Cfar2 0, so we're calling this image and that label and calculating the loss. We haven't performed any training of our model, and here is where we will train the model. So model equals the same thing, and 3,000 to 512, 512 to 2, learning rate 0.02, 100 epochs. Now this is how we're cycling through for epoch and range this, and these 3 lines of code are very important for a neural network. They were listed in this figure that I said is important. Evaluate the model forward, 0 the gradient, compute the loss, and accumulate. Actually, it doesn't necessarily have to do with that figure. But first, we're going to use the optimizer on the gradient, calculate the loss, and then update. So they don't match up as perfectly as I wanted, but these three lines of code always have to be there. Here is the optimizer that we're using, stochastic gradient descent. And yeah, so the loss kind of bounced around a little bit for being such a node heavy model. It didn't really just go down, so I guess this wasn't the best setup. I don't know, they didn't like say why in the book, but I think some of the other ones do better. So we'll just try to keep an eye on and try and figure out why that is. It seems like a pretty good neural network. Maybe the learning rate could be lower, and possibly that would help. We could use a different optimizer function. Or perhaps creating a batch size would be better too. Okay, so now this is the data loader. So the train loader equals torch utils.data loader Cfar2 batch size equals 64 shuffle equals true. So this is the line of code where we are creating a batch size, and we're going to just input that same line of code into our box here. Now we're going to define our model. Our optimizer is the same, loss function's the same, and then we go through it. And for this one, it did a lot better. This one you have it an order of magnitude better, it would appear. And what was the differences? I guess the difference is that we're using a batch size now, so that made it better. Maybe this one's only updating after each epoch, which would not be good for epoch and range in epochs. Out equals model, okay, and loss function equals the loss function of the out and the torch tensor of the label. So what's the difference between those two? And based on that, it's calculating the loss. So for this one, it's updating the gradients after each epoch. In this one, it's updating the gradients after every 64 images. So this appears to be the better method, and we don't really see a convergence though. It hangs around the same. I mean, it starts to drop here in the 80s, so it is going down further. It goes down another order of magnitude. So that did a lot better. Let's see what they do in the next line of code. Same setup again. We're doing a 2-layer network, a log softmax, and LL loss. This is just the same exact thing, it would appear. Huh. I wonder why they would. Let's copy this. Control C. And then here, I'm going to press A to add a box above it. I'm going to paste it so we can just kind of see. Torch, of course all that's going to be the same. Batch size 64. Oh, here's the difference. Okay, so this one has 128 in the second layer. And this one has 512. So this is a more dense network here. But all the other parameters are the same. And are we doing better? Yeah, we're doing better. Look, we end on a better loss. So I think we're doing better with that. So by adding more nodes into the second layer, the network does perform better. Now we're going to do this, where we're determining the accuracy. And this will be the accuracy of the most recent neural network that we did. So we're only doing it for this one, which was the best one. It had the best accuracy. Batch size 64 and 3000 to 512 in the first layer, 512 to 2 in the second layer. We run that, and you can see that it's got an accuracy of 0.99. Now here we're looking at the validation. So this is the Cfar2 validation set, and we can see that on our validation set we get a 0.813. So if you remember, if you have about 100% accuracy on your training set and your validation set isn't at 100% accuracy, then you are probably overtraining. And you're definitely overtraining if it's at 80% accuracy. That's a big difference. That's 100% to 80%. So what we have here is an example of an overtrained model. So I guess to combat that, we're going to go ahead and increase the layers of the network. So now we're going to a 4-layer network, 3000 to 1024 in the first layer, 1024 to 512 in the second layer, and all the way down to this layer. And what these two lines of code are signifying are the same thing, because this is a log softmax and this is a loss function equals in cross entropy loss. So they're just putting these two lines in to say, hey, this is the same thing. And what do we do here? For our loss function, we have the cross entropy loss. So we're sticking with that batch size of 64. We're running the 4-layer network. We're keeping the same learning rate, same number of epochs. We're running this. And are we doing better? Yeah, we're doing better. I'm seeing more zeros down here. So doing pretty good there. But now we will see on the comparison between the training set and the validation set. So it looks like we got an accuracy of 100% on the training set and an accuracy of 80% on the validation set. So again, we're overtraining. We're definitely overtraining. Now this is where they take the sum of the parameters. This is the line of code that they use to do that. It is in the book here. Just so you can do a quick calculation, like how many parameters do I have? Like just to get a brief estimation on what your computation times are going to be looking at. So this is the number of parameters for the 2-layer network, where we're going from the 3000 or whatever to 512 or whatever it is. And this is the computation for the 4-layer neural network. They have it written twice here. Maybe they were planning on doing it for both, but it doesn't work. They name every model. So if they didn't do that, if they didn't say model here and they put like model 1, model 2, model 3, we could go back and have access to each model. But we are creating a new model essentially every time, so we can't go back and check the parameters in each one. The first model is okay, so now they're doing that. Exactly what I said. First model equals in sequential linear 3000 to 512 to 512, and the number of parameters is p nummel. I don't know what nummel means, but it's p dot nummel for p and first model parameters. Do they mention what that nummel is? We can call the nummel method. I don't know how they came up with that word nummel, but just know that that is going to count the number of parameters within the system. So, and it looks like we could do it a few different ways. If you don't remember, if you don't want to write this whole thing, you could just say p in linear 3000 512 dot parameters, or how many are in this one, 3000 to 1024. Okay, so there's a bunch there. Okay. Linear equals in linear 3000 to this one. What's the weight shape? If you remember, the weight is going to be for both of them, but the bias is only going to be for the outputs of them. So the bias shape is only 1024, whereas the weights are applied to both. The weights are the W and the biases are UB. Y equals mx plus b. Your m is a W, and that's the weights. The b is the bias, so it's just a scalar value. Now they start talking about convolutions. So they don't talk about convolutions in the chapter. So it's not the best idea to get into this, but basically it's somewhat of an image transform. When we do these convolutions, we are just manipulating the tensor for a number of reasons. Hopefully they go into a good definition of that in chapter 8. But here we have a different weight shape after performing the convolutions, a different bias shape, so on and so forth here. Do we train a convolutional neural network? I don't know. I don't know if we actually do that or not. Pool. So the way convolutions work is there are convolutional layers followed by max pooling layers. This is where the code did not work. So I'm not sure why. We're just defining a model here. Perhaps it's this ... I don't know what that would signify. And we'll get into what the padding in the kernel size is in the next chapter. But when we're talking about image classification, image segmentation, convolutional neural networks are the way to go. So it's a very important thing, and we'll see that when we start getting higher accuracies with less training time. So yeah, they're saying missing something here. They want us to put that in there? This in tan. I mean, that's what's missing. Oh, maybe that's not what's missing. Well, we'll learn in the next chapter and get that squared away. Let's see if they... Okay, so here's a... Okay, this is a convolutional neural network here. And we're going to go ahead and train that. And let's see if the loss does get better. So the loss is similar, but let's see. Accuracy 96. And the validation is accuracy 90%. So that's the power of a convolutional neural network. We're not overtraining our model. So that's the benefit of utilizing those. And again, the next chapter is on convolutional neural network. They just throw this part of the code in there, I guess, to give us a little bit of a warm-up and get ready for the convolutional neural networks, which are to come in the next chapter. So let's do a little experiment up here with our best network. This one. What happens if we just do 100, 100, 100, 50, 50, 50. So I'm not sure why that doesn't work. We're going from 100 to 50 to 50, 50 to 50 to 2. Let's see. What if I said... Still doesn't work. So this is the common issue. I'll look into this and see if I can get a smaller neural network to work. But this is a very frequent occurring issue when being the architect of your own neural network is the shapes of the matrix not working. So that's when you need to resize them. Okay, well that's it for this lecture, and I'll see you in the next video, which will be Chapter 8. Thank you.